The subject I want to explore with you is simple to name, but vast in consequence: cosmic collisions. They are the engine behind much of the structure, chemistry, and history of our universe. If you look closely at almost any astronomical phenomenon, from auroras above Earth to the formation of stars inside distant nebulae, to galaxies reshaping each other over hundreds of millions of years, you will find some form of impact, compression, or gravitational encounter at its core. My first exposure to this idea came not from a telescope, but from examining the scientific record of Earth itself. Our atmosphere glows during geomagnetic storms because solar particles strike it with measurable force. Our planet orbits with the help of a moon formed after a colossal impact in the early solar system. And the biological landscape that allows you and me to exist was shaped by an asteroid large enough to reset the planet's evolutionary path. None of this is speculative. It is well-supported evidence drawn from missions like NASA's Juno and Galileo ESA's Gaia Observatory, and decades of geological and atmospheric research on Earth. This awareness changes how you see the universe. Instead of picturing a silent, empty expanse, you begin to recognize a system in motion: gas clouds compressing into stars, black holes disturbing the space around them, galaxies passing through each other like transparent ghosts, except for the dense gas that cannot pass so easily. Even the quiet night sky above you is the product of repeated encounters billions of years old. And the best place to begin is with the kind of collision you can actually observe from Earth if you know where to look: the meeting between the solar wind and our atmosphere, the event that produces the auroras. There's a certain honesty in the way Earth responds to the forces flowing through its environment. When I study the upper atmosphere, I keep returning to a simple observation: light appears only when something has been pushed out of balance. You can see that principle at work in the glow of a neon sign or the flicker inside a fluorescent tube. And you can see it on a planetary scale when the sky brightens near the poles. The atmosphere radiates color because it has been struck subtly, compared with geological violence, yet forcefully enough that atoms cannot remain in their usual calm states. They absorb energy, hold it for a moment, and then release it as visible light. That process is the quiet signature of a collision. Most people treat auroras as gentle decoration. If you've stood beneath one, you probably experienced it as something soft drifting, almost weightless. Intuition pushes you to categorize it as a passive glow, something that simply happens when conditions are right. Few imagine particles arriving at tremendous speeds funneled into the poles by Earth's magnetic field. Even fewer picture those particles slamming into oxygen and nitrogen atoms with enough energy to rearrange their internal structure. The mind tends to interpret smooth, graceful motion as something free of force, but the evidence we have today tells a different story. Measurements from NASA's Themis mission and ESA's cluster spacecraft reveal a constant stream flowing outward from the Sunday. This stream, known as the solar wind, consists mainly of charged particles that escape the outer layers of the sun and travel across space at hundreds of kilometers per second. Under normal solar conditions, the flow is steady but moderate. During more active periods, such as coronal mass ejections, the density and speed of the wind increase dramatically. The interactions Earth experiences during those events can shift rapidly, sometimes within minutes. Earth's magnetic field plays the role of a shield. It wraps around the planet and bends most of the incoming particles away. But the field is not uniform. At high latitudes, the magnetic lines of force converge and dip downward into the atmosphere. Charged particles spiral along those lines, gaining speed as they descend. When they reach altitudes around 100 kilometers, they encounter the thin but significant layers of atmospheric gas. This is where collisions begin. Electrons and protons from the solar wind transfer energy to atmospheric atoms. The electrons inside those atoms jump into higher energy configurations. They do not remain there long. When they fall back into their stable states, they emit light. The color depends on both the type of atom and the altitude of the collision. Oxygen produces green light at lower altitudes and red light at higher ones. Nitrogen produces blue and violet hues. All of these emissions match laboratory measurements of atomic spectra, providing direct confirmation of the mechanism. During strong geomagnetic storms, the process intensifies. The auroral oval, normally confined to high latitudes, expands toward the equator. At times, observations from GOES satellites have shown disturbances wrapping around the entire magnetic field in complex patterns, leading to auroras visible in regions where they are usually absent. Each glow, ripple, and fold in the light corresponds to variations in the flow of incoming charged particles. The aurora's movement is not random. It is shaped by the constantly shifting electromagnetic environment. To visualize the entire chain of events, imagine standing far above Earth, perhaps at the altitude of a weather satellite. Below you, the magnetic field extends like an invisible bubble distorted by the solar wind. Where the wind presses harder, the bubble compresses. Where it relaxes, the bubble stretches back outward. Now picture streams of high-speed particles sliding along those magnetic lines. As they near the poles, the field channels them downward. They enter the atmosphere like rain entering a funnel. At each collision with an atmospheric atom, a tiny flash occurs far too small to see individually. But multiplied by trillions, the flashes merge into sweeping curtains of light. From ground level, the display seems almost slow, as if the sky were breathing. From orbit, the activity is much more dynamic. Instruments aboard the International Space Station, record waves of brightness, racing across the polar regions in seconds. The scale is difficult to appreciate without numbers, but the auroral oval can span thousands of kilometers. It is a structure larger than many countries combined, shifting constantly as Earth interacts with its star. Encounters with this phenomenon leave different impressions depending on how you experience them. You might remember a night when the sky seemed alive, reshaping itself in a silence that felt out of proportion with the intensity of the colors above you. For me, the experience often comes through data streams curve representing particle energy, magnetic field strength, and atmospheric emission profiles. Yet both experiences point to the same truth: Earth is part of a larger environment. It feels stable, but it is continuously influenced by forces arriving from beyond its atmosphere. Those forces are not abstract. They leave visible marks. The aurora is one of the rare cases where a collision in space produces a display safe enough for you to stand beneath. Most other collisions in the solar system do not share that property. They involve far more mass, far more velocity, and far more energy. When even a small asteroid approaches Earth, the consequences depend on details like its size, composition, and speed. The same physics that governs a gentle glow in the sky energy transferred through impact can determine whether a space rock simply burns up or releases enough energy to reshape landscapes. When the solar wind meets the atmosphere, the result is color. When larger objects meet Earth, the outcome is very different. The next step in understanding cosmic collisions is to examine what happens when an asteroid is on a trajectory toward our planet. The same principles remain, but the scale changes dramatically. There is a recurring question that surfaces whenever people think about cosmic collisions: would humanity actually notice an incoming asteroid early enough to respond? It sounds simple, almost like asking whether you would notice a car coming down the street. But asteroids approach from all angles. They reflect very little sunlight, and they do not announce themselves with any obvious signal. When I look at the sky through the perspective of planetary defense research, I'm reminded that Earth is moving through a dynamic environment filled with large and small remnants from the solar system's formation. Most of them pass harmlessly, but a fraction do not. And the challenge is distinguishing the harmless from the hazardous. Many people imagine the scenario through the lens of science fiction films. Those stories tend to portray every asteroid as a global threat, usually accompanied by fiery impacts, shock waves sweeping across continents, and a countdown timer. That intuition makes sense when all you see are cinematic disasters. It also leads to a common misconception: the belief that any large rock from space will devastate Earth on arrival. But the evidence we have today tells a different story. Astronomers track thousands of near-Earth objects, or NEOs, using surveys such as NASA's NEOWISE mission and the Pan-STARRS telescopes in Hawaii. These instruments detect faint points of light moving slowly against the background stars. By measuring how those points shift night after night, researchers calculate orbits, predict future positions, and estimate sizes. The majority of these objects measure only a few meters across, too small to reach the ground intact. Larger objects, tens to hundreds of meters wide, are far less common, yet they carry enough energy to cause regional damage if they enter the atmosphere at high speed. The rarest class, those kilometers across, are the ones capable of global consequences. Fortunately, nearly all known objects of that size are cataloged, and none pose an immediate risk. When an asteroid approaches Earth, the key question becomes its closing velocity, the speed at which it approaches relative to Earth's own motion. Even a modestly sized object can carry tremendous kinetic energy because it arrives at tens of thousands of kilometers per hour. Kinetic energy grows with the square of the velocity, meaning that doubling the speed quadruples the energy delivered. But unlike explosives here on Earth, the destructive potential comes not from chemical reactions inside the object, but from the object's motion itself. Every bit of that energy must go somewhere the instant the asteroid slows to zero on impact. Before that moment, astronomers estimate where the object will strike by projecting its orbit forward. Because small uncertainties in the position accumulate over time, the predicted impact site stretches into what researchers call an uncertainty ellipse. It is narrower along one axis and longer along the direction of travel. This shape reflects a simple fact. It is easier to determine how far left or right an object will fall than it is to know exactly how far along its trajectory the collision will occur. Missions like NASA's DART and ESA's Hera are helping narrow these uncertainties by teaching us how asteroids respond to forces such as gravity, sunlight, and impact deflection. A striking example of unexpected impact behavior came in the year 2013 with the Chelyabinsk event in Russia. A roughly 20-meter-wide object entered the atmosphere at high speed, releasing an intense shockwave as it fragmented. The explosion occurred far above the ground, yet the resulting pressure shattered windows across hundreds of square kilometers. Thousands of people were injured, not by the asteroid itself, but by flying glass. Dashcam footage captured the event from multiple angles, giving scientists a rare opportunity to study the dynamics of an airburst in detail. To picture what happens during an asteroid encounter, imagine following the object from a vantage point tens of kilometers above Earth. The asteroid enters the atmosphere wrapped in a sheath of compressed air. The front surface experiences intense heating. If the object is made of weaker material stone rather than iron, the stresses exceed its structural strength and it breaks apart. Those fragments then generate additional shock waves as they decelerate violently. If the asteroid is large enough or strong enough to reach the surface, the final impact releases all remaining kinetic energy. In a fraction of a second, excavating a crater and vaporizing most of the incoming mass. From ground level, detecting a threat depends on coordination, communication, and preparation. If astronomers identify a medium-sized asteroid on a collision course days or weeks in advance, evacuation becomes the most practical response. Consider the daily movement patterns of a large metropolitan region. Millions of people routinely flow in and out within hours. Redirecting that flow away from a predicted impact zone is challenging, but not impossible. The greater difficulty lies in recognizing the threat early enough to act. Whenever I speak with people about planetary hazards, I notice how strongly intuition shapes their expectations. You may assume that the sky is fully monitored or that any dangerous object would appear bright and obvious. But many asteroids are dark, reflecting only a few percent of the sunlight that hits them. Some approach from the direction of the sun, making them nearly invisible to ground-based telescopes. These realities remind me that vigilance requires sustained effort, not passive confidence. Thinking about asteroids often brings a mix of unease and clarity. Unease, because the forces involved are immense. Clarity, because understanding those forces removes much of the mystery. When you or I look at a moving object on Earth, we judge its danger by its size and appearance. In space, size alone tells only part of the story. The real question is how much energy the object carries. That perspective shifts the focus from fear to physics, from uncertainty to measurable quantities. The collisions that shape planetary surfaces and alter climates begin with simple ingredients, mass, velocity, and structure. Up close, these ingredients define whether an object shatters in the sky or reaches the ground. The next step is to examine why some asteroids explode on impact, even though they contain no explosive material at all. Understanding that mechanism brings the physics of cosmic collisions into sharper focus. A question that often surprises people is why an asteroid can explode with the force of a weapon, even though it contains no chemical fuel. It seems counterintuitive. A rock, after all, is just a rock. If it falls from the sky, you might assume it simply hits the ground and leaves a crater. That intuition comes from experiences with familiar objects, stones, debris, even falling trees. But the conditions under which asteroids strike Earth differ dramatically from anything we encounter in our everyday surroundings. In ordinary life, objects fall at speeds limited by air resistance. A dropped stone might reach a few tens of meters per second. At that speed, the impact is localized. The stone stops, the ground compresses, and the energy disperses quickly. It feels logical to extend that experience to cosmic rocks. But the evidence we have today tells a different story. Asteroids approach Earth at extraordinary speeds. Even an object entering purely under Earth's gravity arrives at roughly 7 miles per second. Many come in faster because they already possess orbital motion of their own. When Earth and an asteroid move toward one another at the right orientation, their velocities combine. Closing speeds of 10 or more miles per second are common. This matters because the energy carried by an object increases with the square of its speed. If you were to double the speed of a falling rock, the energy delivered on impact would not merely double, it would quadruple. To understand what happens at the moment of impact, it helps to think about where the energy goes. Before the collision, the asteroid's motion stores all of its kinetic energy. After the collision, its speed becomes zero. That energy must be absorbed or transformed in an instant. The ground beneath the asteroid absorbs some of it, but much of the energy travels back into the asteroid itself, and this is where the physics becomes decisive. Inside any solid object, whether a metal sphere or a porous, stony meteorite, the atoms and molecules are bound together by electromagnetic forces. You could imagine them as countless microscopic hooks holding each other in place. The strength of those bonds defines what physicists call the binding energy. If the energy delivered to the object exceeds that binding energy, the structure cannot remain intact. At terrestrial impact speeds, the kinetic energy of an asteroid far surpasses the energy holding its material together. That imbalance guarantees that the object will not merely crack or fracture, it will undergo a catastrophic breakup. Scientists refer to this as a high-speed impact regime. In slow collisions, like 2 billiard balls, the objects remain recognizable afterward. But at extremely high speeds, the impact compresses the object faster than it can deform. Temperatures spike to thousands of degrees within microseconds. Shock waves propagate through the body of the asteroid and through the surface of the planet. The asteroid essentially disintegrates from the inside out as the incoming energy overwhelms every bond that once held it in a single piece. This insight explains why impact craters on the moon and other planetary bodies are nearly perfect circles. The explosion, because it truly is, an explosion is symmetrical. Even if the asteroid strikes at a shallow angle, the intense isotropic release of energy produces a round crater. NASA's studies of the Barringer crater in Arizona show that the iron meteorite responsible vaporized almost completely. Researchers found metallic droplets scattered around the site, but the original body itself was reduced to tiny fragments and plasma. The same principle applies on much larger scales. The Chicxulub impactor, which struck Earth roughly 66 million years ago, left a crater more than 100 miles across. Geological evidence indicates that the object itself did not survive the collision. A mixture of rock vapor, molten droplets, and fine dust filled the atmosphere. None of that requires chemical explosives. It arises entirely from converting motion into energy during a single abrupt stop. To visualize this process, imagine standing far above Earth, watching an asteroid approach. As it nears the surface, its kinetic energy becomes intensely concentrated. In the final milliseconds, the object decelerates from cosmic speeds to zero. The ground at the impact site is forced downward, sideways, and upward in rapid sequence. Material is ejected upward like a plume, reaching heights greater than the tallest mountains. Shock waves travel outward across the landscape. The asteroid itself, compressed more violently than any industrial press could achieve, transforms into superheated gas. Now, imagine scaling down to the microscopic level. The individual bonds that once held the asteroid together experience forces far beyond their limits. They snap not one by one, but collectively releasing fragments that themselves collide at high speed. The idea of an exploding rock becomes less mysterious when you think of it as a structure collapsing under more energy than it could ever withstand. Events like this remind me how human intuition is shaped by slow-motion earthly experiences. A falling branch or piece of debris carries too little energy to behave any differently. Our eyes and instincts evolved in a world where objects rarely exceed a few hundred kilometers per hour. When you or I look at a cosmic rock, our instincts underestimate the energy because we are not built to imagine objects moving at tens of thousands of kilometers per hour. Yet, understanding that mismatch brings a certain clarity. We can appreciate that the energy governing these events is not exotic or hidden. It is the same kinetic energy that moves every object in motion. The only difference is scale. A small asteroid traveling faster than anything on Earth releases in an instant what would otherwise require vast chemical or mechanical processes. This perspective also prepares us to understand why not all asteroids reach the ground intact. Many detonate in the atmosphere when the stresses exceed their structural limits, creating what scientists call airbursts. Those airborne explosions carry their own distinctive signatures, shock waves, bright flashes, and sudden bursts of heat. To explore those events, we shift our attention from ground impacts to the high altitudes where many cosmic collisions unfold. Most people imagine an asteroid as something that streaks through the atmosphere and plunges all the way to the ground. The intuition is understandable. Gravity feels relentless, and objects that fall toward Earth generally complete their journey. But many incoming space rocks never reach the surface. Instead, they break apart high above the ground in what scientists call an airburst, a sudden release of energy that can rival the power of a ground impact. The idea of an explosion occurring before the object touches anything seems at first glance contradictory. A rock doesn't normally burst open in midair when you drop it. Trees, buildings, and mountains absorb collisions only when an object physically reaches them. That simple logic shapes the way we imagine falling objects. But the evidence we have today tells a different story. When an asteroid enters the atmosphere at cosmic speeds, the air in front of it cannot move aside quickly enough. It compresses to extreme pressures, heating the air and the asteroid's surface. That compression shock is intense, far stronger than anything produced by a supersonic aircraft. As the asteroid descends, the atmosphere becomes denser and the forces acting on it grow rapidly. If the internal structure of the object is weak, porous, or fractured, the stresses exceed its strength long before it reaches the ground. NASA's analysis of the Chelyabinsk event in the year 2013 illustrates this clearly. The incoming asteroid, about 20 meters across, fragmented at an altitude of roughly 30 kilometers. The breakup occurred because the mechanical strength of the rock could not withstand the dynamic pressure. When the force of air pushing against the object becomes greater than the force holding it together, the structure fails. The result is not a gentle disintegration, but a sudden violent release of energy. During an airburst, the asteroid's kinetic energy is transferred into heat, light, and pressure. A shock wave propagates outward and downward. People near Chelyabinsk reported a brilliant flash bright enough to cast shadows, and a wave of heat felt on their skin. The shock wave arrived later, breaking windows across thousands of square kilometers. Although the object never struck the ground, more than 1,000 people were injured by shattered glass. Historical accounts show that airbursts are not rare on geological timescales. The Tunguska event in the year 1908 flattened forests across Siberia, even though the object likely exploded tens of kilometers above the surface. The energy released was comparable to a large thermonuclear device, yet no crater formed. The forest floor bore only evidence of downward pressure consistent with a massive blast wave passing overhead. These events demonstrate that the distinction between an impact and an explosion is not always tied to contact with the Earth itself. The decisive factor is how rapidly kinetic energy is deposited. For an airburst, the atmosphere acts as both a decelerator and a trigger. As the asteroid compresses air in front of it, the resulting thermal and mechanical stresses grow until the object can no longer maintain its cohesion. To visualize this process, imagine yourself far above Earth, watching an asteroid descend through layers of atmosphere. At first, it glows faintly as frictional heating begins. As it drops lower, the glow intensifies into a streak of bright white light. The air in front of the object forms a cone of compressed gas hotter than molten metal. The asteroid deforms under the stress, microfractures spreading through its interior like cracks in porcelain. When the pressure reaches a critical threshold, the structure fails. The object breaks apart almost instantaneously, converting its remaining motion into a burst of heat and light. From the ground, the event unfolds in a surprising sequence. Light arrives, first intense, brief, and often accompanied by a flash that saturates cameras. Moments later, the shock wave hits. It expands outward like ripples on a pond, except these ripples travel through air at hundreds of meters per second. The sky may appear to shimmer as the wave distorts the light passing through it. In places directly beneath the detonation, the downward pressure can snap trees or damage structures without leaving a crater. One reason we understand modern airbursts so well is the abundance of dashcam recordings, particularly in countries where drivers routinely equip their cars with forward-facing cameras. These devices inadvertently became scientific tools. They provided researchers with multiple vantage points, allowing triangulation of the trajectory, brightness, fragmentation, altitude, and energy release. The Chelyabinsk asteroid became one of the most precisely documented natural explosions in history, not because scientists planned it, but because daily life happened to generate the data. You and I rarely think about how often technology captures events beyond our intention. But moments like this reveal how much information enters the scientific record through everyday human habits. Instead of relying solely on telescopes or satellites, researchers gained access to dozens of independent recordings, ordinary citizens inadvertently documenting an atmospheric collision at cosmic speeds. Airbursts also reshape how we think about planetary hazard. Many people imagine an asteroid threat as a single impact point on a map. But smaller objects pose a different kind of risk. They may explode far above the ground, extending their effects over a broader region. The absence of a crater does not imply the absence of danger. The Tunguska and Chelyabinsk events show that energy delivered from above can be both widespread and unpredictable. Understanding airbursts also helps refine our expectations for future encounters. If an object is small, weak, and fast, the atmosphere may protect the ground by forcing the energy release at high altitude. If an object is larger or structurally stronger, it may survive long enough to reach the surface. Distinguishing between the two requires accurate knowledge of composition speed and angle of entry details that planetary defense programs continue to study through missions like NASA's NEOWISE and the expanding network of sky surveys. That brings us naturally to an even larger question. If airbursts demonstrate how destructive a relatively small object can be, what happens when we step beyond the scale of individual rocks and consider collisions shaped by entire galaxies, structures containing billions of stars moving under mutual gravity? When people hear the phrase galaxies colliding, the mind often leaps to the most dramatic interpretation, countless stars smashing into one another like a cosmic demolition. It is an understandable image. A galaxy seems dense when you see it in a photograph or an astronomy illustration. Billions of stars compressed into a luminous spiral give the impression of a crowded metropolis. From that intuition, collisions seem inevitable. But the evidence we have today tells a different story. A star is enormous in its own right, yet the distances between stars are larger still. If you scaled a star down to the size of a pea, the nearest star would be hundreds of meters away. The Milky Way looks dense only because it is bright. Light collapses distance in our perception. Brightness feels like concentration. But in physical space, a galaxy is mostly emptiness. That is why, even when two galaxies pass directly through one another, their stars almost always keep going without interruption. They sail on through, influenced only by gravity, not by physical collisions. Yet something significant does collide. Interstellar gas, vast clouds of hydrogen, helium, and trace elements cannot pass through itself the way stars do. Gas behaves differently. When two gas clouds meet, they compress heat and accumulate. Their motion changes abruptly as the clouds interact. NASA's Hubble Space Telescope and the James Webb Space Telescope have captured many examples of this phenomenon. Two galaxies stretching and twisting each other into new shapes, their stars gliding past like lanterns on invisible currents, while their gas forms tangled bridges, filaments, and glowing knots. One of the clearest demonstrations comes from simulations created by researchers at institutions such as the Harvard-Smithsonian Center for Astrophysics. These models track the movement of millions of particles representing stars, gas, and dark matter. When the two modeled galaxies intersect, the stars trace graceful arcs continuing along altered trajectories. But the gas slows, abruptly piling up in regions where clouds collide. Those compressed regions ignite new activity, shockwaves, turbulence, and eventually the birth of new stars. To visualize the moment of collision, imagine two spiral galaxies drifting toward each other. From afar, the shapes appear serene. But as they approach their gravitational fields, begin a slow negotiation. The outer stars feel a slight tug, causing the spirals to stretch into long tails. When the galactic disks overlap, the stars barely notice anything other than the shifting pull of gravity. They continue on paths that curve smoothly around the merged mass distribution. Gas clouds, though, have no such freedom. They forcefully meet, heating to temperatures that cause them to glow. The regions of collision appear as luminous knots, embryonic star-forming sites responding to the pressure of compressed gas. Seen from inside, the experience would be very different from the chaos people imagine. If you were living on a planet within one of the colliding galaxies, you would not witness stars slamming into each other. Instead, over millions of years, the night sky would gradually shift. Constellations would distort, new patterns would unfold, and a faint arc of light made of stars from the approaching galaxy would stretch across the sky. The collision from a human perspective would be a slow and quiet reshaping of the heavens. What makes these events scientifically powerful is the way they reveal the hierarchy of interactions in the universe. Stars behave as collisionless particles. Gas, by contrast, is collisional. And dark matter, which forms massive halos around galaxies, passes through everything almost without interaction at all. This separation of behaviors allows astronomers to study each component in isolation. Observations of colliding galaxies show bright ribbons of gas, where it clumps and slows, and faint traces of stars where they drift independently. Dark matter, detectable only through its gravitational effects, forms an invisible skeleton guiding the motion of all other components. One of the most striking real examples is the antennae galaxies. When you look at Hubble's images of them, you see long arcs of stars flung outward by gravitational tides in glowing regions of gas where clouds have collided. These structures are not aesthetic flourishes. They are signatures of energy transfer, momentum exchange, and gravitational rearrangement. Over time, the two galaxies will settle into a single, more rounded shape. A new galaxy formed from the merging of the original pair. Living inside a galaxy, you and I rarely sense that we inhabit something dynamic. Our world feels stable. Our sky feels fixed. But galaxy collisions remind us that stability is temporary. On the largest scales, structure evolves. Nothing in the cosmos is locked in place forever. Even the Milky Way is on course to merge with the Andromeda Galaxy in several billion years. Observing these collisions also emphasizes the limits of our intuition. The idea that two colossal systems can pass through each other without stars touching challenges the way our senses interpret density and brightness. Our perception is tuned for Earth objects we encounter here occupy space in familiar ways. But in the cosmos, the proportions are different. Emptiness is the dominant ingredient. Light compresses that emptiness into a misleading picture. Instruments help us see the true scale. Astronomers rely on telescopes across many wavelengths to study these interactions. Optical observatories reveal the stars. Infrared telescopes trace the dust warmed by newborn stars. Radio observatories detect cold gas being compressed. X-ray observatories show the hot gas produced by violent interactions. By combining these views, scientists build a layered understanding, each wavelength telling a different part of the story. Thinking about this reshaping of galaxies raises an important connection. Compressed gas does not simply heat and glow. Under the right conditions, it forms stars. Collisions, rather than destroying structure, can ignite new generations of stellar light. The next stage in this sequence lies in understanding how pressure and gravity convert cloud-like matter into brilliant, long-lived suns. Galactic collisions often sound catastrophic, but one of their most remarkable outcomes is creation rather than destruction. When I first learned that smashing clouds of gas together can produce newborn stars, it challenged an assumption I didn't even know I was carrying. Collisions in everyday experience tend to break things. They do not assemble complicated structures. Yet in astronomy, the opposite is frequently true. Under the right conditions, encounters between gas clouds can become the beginning of something luminous, long-lived, and stable. Most people imagine a star forming quietly, almost delicately somewhere in a dark nebula. And that does happen. Gravity can gather material slowly over millions of years, creating dense pockets within molecular clouds. But the evidence we have today tells a different story about many star-forming environments. Observations from ALMA in Chile, from the Chandra X-ray Observatory, and from the Hubble and James Webb Space Telescopes repeatedly show that some of the brightest, most intense bursts of star formation are triggered by collisions. In regions where galaxies interact, gas clouds do not drift past one another peacefully. They compress, fracture, and cool. And in that compression lies the seed of stellar birth. To understand why, imagine a broad cloud of cold hydrogen gas floating through a galaxy. On its own, it may be stable for long periods, but stability in a gas cloud is delicate. Gravity pulls inward, trying to collapse the cloud. Pressure pushes outward, trying to keep the cloud expanded. If pressure wins, the cloud drifts aimlessly. If gravity wins at one small point, that region collapses and begins the long process of becoming a star. When galaxies collide, or when gas streams flow through each other, pressure conditions change abruptly. Collisions push gas into tighter volumes faster than it can respond. The balance tips. Local density rises, and gravity, now unopposed, pulls the material inward. This process is sometimes called shock compression. A shock is simply a region where gas is compressed faster than information can travel through it. In the aftermath, temperature briefly jumps, but radiative cooling light escaping from the heated gas allows the cloud to shed heat and remain dense. ALMA has shown these compressed ridges in interacting galaxies where long strands of gas are squeezed into narrow lanes. In those lanes, gravity takes over efficiently. Stars form not one at a time, but in clusters. When this happens at a galactic scale, astronomers call the result a starburst. Starburst galaxies shine intensely in infrared wavelengths because their newborn stars heat the surrounding dust. It helps to picture this visually. Imagine two diffuse clouds drifting toward one another thousands of light years across. Viewed from the outside, they move gracefully like mist being pushed by gentle wind. But at the moment of contact, the internal motions change. Gas grains slow as they meet material moving in the opposite direction. The front edges glow faintly as heat builds, and behind that glowing boundary gas gathers into a thick rope-like structure. Inside that structure, gravity begins drawing knots of matter inward over time long by human standards. But brief in cosmic terms, those knots grow denser and hotter until fusion ignites. What began as a collision ends as a collection of shining stars. For a moment, consider what those stars represent. They are factories of heavier elements. They generate radiation that shapes their surroundings. They eventually explode in supernovae that enrich space with the building blocks of planets. Collisions do not merely spark light, they define chemical evolution. Without them, galaxies would become quiescent, their gas slowly drifting, never compressed enough to ignite sustained star formation. The personal side of this is subtle but real. When I think about how ideas form in the human mind, I sometimes see an echo of this process. You and I gather experiences, bits of information, fragments of understanding. They can remain separate for years, drifting like the components of a gas cloud. But when two pieces of information meet in the right way, when they collide with just enough force, they compress into something new, a more stable thought. A clearer insight, not unlike a star forming from the density created by impact. It is not a mystical parallel. It is simply a reminder that creation often follows pressure and interaction, not isolation. Astronomers study this process across many wavelengths. Infrared observations reveal the warmth of dust near newborn stars. Radio observations show the cold gas feeding future star-forming regions. X-ray data from Chandra highlights where high-energy processes heat surrounding matter. Together, these instruments confirm the same picture: collisions accelerate star formation by rearranging matter into gravitationally unstable shapes. One particularly valuable example is the antennae galaxies, which I mentioned earlier. They contain regions where star formation is occurring at tens or hundreds of times the rate of the Milky Way. The cause is clear: heads of gas clouds meeting and compressing in the aftermath of the galactic encounter. JWST has provided even sharper images of these clumps, revealing the earliest stages of cluster formation within them. The story becomes even more intriguing when we consider what does not collide. In the same environment where gas clouds slam together, dark matter halos pass through each other almost unchanged. Stars glide through mostly unaffected. The separation of behaviors, collisionless stars, collisional gas, and non-interacting dark matter creates a layered structure. Each component shapes the evolution of the system in different ways. What collides becomes luminous, what passes through shapes the gravitational environment around the collision. In reflecting on this, I find the outcome both inevitable and beautiful. Collisions are not interruptions in cosmic order. They are part of how order arises. Where gas meets gas pressure and gravity begin a new cycle. The next step in our exploration asks, what happens to the components that do not collide, components like dark matter, which move through these dramatic events as though nothing occurred at all? When I first encountered the idea that most of the matter in the universe does not collide, I found it surprisingly counterintuitive. We are used to thinking of matter as something you can bump into. Even air resists our motion ever so slightly. Water pushes back more strongly. Rock, metal, and flesh resist almost completely. So the notion that the majority of mass in the cosmos behaves like a ghost passing through galaxies, gas clouds, and even other dark matter without slowing forces a shift in intuition. If collisions shape so much of the visible universe, why is dark matter exempt at a human scale? Anything that occupies space seems destined to interact. But the evidence we have today tells a different story. In the early 2000s, researchers studying a system known as the Bullet Cluster uncovered one of the clearest demonstrations of dark matter's non-collisional behavior. Two galaxy clusters had passed through each other, gas within them had collided violently, slowing down and heating up. But the majority of mass mapped through gravitational lensing had sailed past the collision zone untouched. The visible matter stayed behind. The invisible matter moved on. This was not an interpretation. It was a measurement. To understand why dark matter behaves like this, we have to recognize that interactions come in categories. Ordinary matter interacts through electromagnetism, which is why gas clouds feel resistance, why atoms stick together, and why stars and planets exist as objects. But dark matter, according to the best current evidence, interacts gravitationally and perhaps through the weak nuclear force, but not electromagnetically. Without electromagnetic interactions, dark matter cannot cling, scatter, or repel in familiar ways. It does not exchange light or charge. It does not feel friction. It simply responds to gravity, while everything else responds to gravity, and the electromagnetic rules that keep particles sticky. Observations by NASA's Chandra X-ray Observatory and weak lensing surveys using ground-based telescopes have mapped this behavior. The gas in colliding clusters glows brightly in X-rays because it heats up during impact, The dark matter, however, shows up only through the distortions it creates in the paths of background galaxies, a technique called gravitational lensing. The separation between these two components is dramatic. In the bullet cluster, for example, the gas lags behind while the dark matter continues forward, dragging stars loosely along with it. This clean separation offers one of the strongest non-laboratory proofs that dark matter exists at all. It helps to visualize the interaction. Imagine two enormous translucent clouds sliding toward each other, each representing a cluster of galaxies. Embedded within them are tiny beads, representing stars, and even tinier grains, representing gas. When the clusters meet the grains, the gas collide with one another, piling up, slowing down, and heating up. The bead stars mostly slip through since space between them is vast. But the most intriguing layer is the faint, shadow-like volume that passes without hesitation. That is the dark matter halo. It enjoys no resistance, as if the universe offered it an open path. One might ask whether dark matter could ever collide. The answer is uncertain. Some theories propose that dark matter might self-interact within narrow limits, producing subtle alterations in how halos evolve. The best current evidence suggests that if these interactions exist, they are extremely weak, far weaker than the familiar collisions of gas. Studies of merging clusters, such as MAX J0025, and the musketball cluster place tight constraints on any such behavior. But for practical understanding, dark matter remains effectively collisionless on large scales. There is a personal dimension to this that I often reflect on. Our senses evolved to detect only the thinnest slice of physical reality. We see light in a narrow wavelength band. We feel forces transmitted through ordinary matter. We hear pressure waves in air, but dark matter interacts through none of these channels. So our instinct that matter should collide comes from the matter we can touch, not from the matter that occupies most of the universe. It's a reminder that intuition is shaped by survival, not by completeness. And when intuition meets data, it must adapt. In cosmic collisions, this difference in behavior leads to profound consequences. The dark matter halo largely preserves its structure after a collision, even when the visible parts of a galaxy gas cloud's dust star-forming regions are violently disturbed. Because dark matter contains most of a galaxy's mass, and therefore most of its gravitational influence, its non-collisional passage determines the long-term shape of the new system. After galaxies interpenetrate and emerge, their dark matter halos slow turn and eventually merge through gravitational interactions alone. The visible parts follow that gravitational choreography, even if they were disrupted during the initial impact. This separation of components is one reason astronomers rely so heavily on computer simulations. Researchers at institutions such as the Harvard-Smithsonian Center for Astrophysics and Durham University have used supercomputers to model galaxy collisions with billions of simulated particles. These models must treat dark matter differently, from gas assigning it no collisional cross-section. A simulation that mistakenly gives dark matter electromagnetic interactions produces unrealistic structures. When dark matter is modeled as collisionless, the simulations accurately reproduce what telescopes reveal about galaxy shapes, halo sizes, and cluster mergers. Another vital point is scale. Dark matter's lack of collisions does not make it irrelevant. On the contrary, its gravitational pull anchors galaxies, stabilizes rotating disks, and prevents young galaxies from flying apart. But its non-interaction means that while it shapes the stage, it does not participate in the choreography of light and gas. It provides the deep gravitational wells that guide the motion of stars, yet it remains invisible, detectable only by its influence. In reflecting on all this, I am struck by how much of the universe operates outside direct human experience. If you or I watched two clouds of ordinary matter collide, we would expect turbulence and resistance. But the cosmos adds another layer, a component that glides smoothly through these events, setting the gravitational framework in which everything else unfolds. Understanding this difference helps us interpret the next step in our exploration: what happens when the most extreme objects in the universe collide. Black holes, unlike dark matter, do not pass silently by one another. they merge. And when they do, the universe itself vibrates. When I think about collisions in the universe, nothing feels quite as counterintuitive as the merging of black holes. For most objects, we imagine a surface, a boundary you could touch if you were reckless enough. But black holes do not offer anything like a surface. Their boundaries, the event horizons, are simply regions of space-time where escape is impossible. So when two black holes meet, people often ask me, what happens to those boundaries? Do they bounce? Do they tear? Do they interpenetrate? The reality is stranger and more elegant than any of those images. It's natural for human intuition to picture the event horizon as a kind of membrane. We grow up handling solid objects. When two of them meet, they resist. They either merge through melting or break apart upon impact. For this reason, many imagine two black holes approaching each other like two cannonballs. But the evidence we have today tells a different story. In 2015, the LIGO detectors in the United States recorded a faint ripple in space-time, the first direct observation of gravitational waves. That signal came from two black holes spiraling into each other over 1 billion light years away. And from that signal, we've learned that their horizons did not collide in any familiar sense. Instead, they gradually fused as space-time reshaped itself around a new, larger gravitational well. The scientific explanation begins with general relativity, Einstein's description of gravity as the curvature of space-time. A black hole is not an object sitting in space-time. It is a region where space-time is warped so much that all possible paths lead inward. The event horizon marks the boundary, where all outward paths curve back. When two black holes draw near, each deforms the curvature around the other. Their horizons, these gravitational boundaries, shift, stretch, and elongate, responding not to contact but to geometry. It's as though two deep wells in a rubber sheet are pulled together. Their surrounding contours distort long before the wells meet. During this approach, energy is radiated away not as light, but as gravitational waves. These waves are ripples in the very geometry of space predicted by Einstein in 1916. They carry energy outward, and because energy is leaving the system, the black holes spiral closer. The signal recorded by LIGO matched this exact pattern, a rising pitch increasing in frequency and amplitude over fractions of a second, ending abruptly when the merger completed. That abrupt end marked the formation of a single larger horizon. Researchers at the LIGO Scientific Collaboration and theorists at institutions including Caltech and MIT spent decades developing models for this process. Supercomputer simulations built on the work of physicists such as Kip Thorne and Saul Tucholsky show that as the black holes near their final orbit, their horizons flatten slightly on the sides facing each other. Then in a final instant, a bridge forms a smooth passage where the boundaries join. The horizon becomes one continuous surface, enclosing a mass greater than the sum of its parts minus the energy carried away by gravitational waves. To visualize this, imagine two soap bubbles floating toward each other. At first, they distort slightly where the thin films feel each other's pull. Then, when they touch the surfaces, merge into one larger bubble. But this analogy fails in one important way. Soap bubbles merge through surface tension. Black holes merge because space-time itself reshapes, smoothing out into a deeper gravitational well. There is no tearing, no cracking, no collision. The horizon does not act like matter. It acts like geometry. The merger also releases an astonishing amount of energy. In the first detected event, roughly, the mass of 3 suns was converted not into light, but into gravitational radiation. That energy flashed across the cosmos, stretching and squeezing space as it passed through Earth. LIGO's detectors, enormous L-shaped instruments with laser beams traveling down vacuum tunnels, measured this stretch as a change smaller than the width of a proton. Yet that subtle vibration opened an entirely new window on the universe, a way to sense cataclysmic events that do not emit light at all. There is a personal dimension to this discovery that stays with me. For the first time, humanity detected a form of cosmic communication that does not rely on photons. Light has been our primary messenger for millennia, carrying information from stars, galaxies, and nebulae. But black holes do not shine. Their mergers would have remained permanently silent to us. without an instrument capable of feeling the tremors of space-time. In 2015, we didn't see the collision. We heard it in a sense more abstract than sound, but equally profound. It reminded me that our sensory limitations are not final. Technology can extend perception far beyond the biology that shaped us. In the years since LIGO Virgo and Kagra have detected dozens more black hole mergers, the patterns reveal details about the masses involved, the spins of the original black holes, and the properties of the final horizon. Each detection strengthens our confidence in the underlying physics, and each event teaches us that even the most violent gravitational encounters follow clear, predictable rules. Geometry absorbs the drama, smoothing it into a peaceful final configuration. At this point in our exploration of cosmic collisions, the contrast with dark matter becomes even clearer. Dark matter passes through the universe unaffected by electromagnetic forces. Black holes, on the other hand, reshape space-time so profoundly that when they merge, the universe itself vibrates. Their collisions produce no light, no debris, no fragments, only a new horizon and a brief tremor in the fabric of reality. Understanding this prepares us for another question that often arises: if gravitational waves can be recorded and converted into audio signals we can listen to, does that mean the universe is filled with sound? Or are we translating something that has nothing to do with sound in the first place? That question leads us directly into our next step. People often ask me whether the universe is noisy. After hearing that gravitational waves from black hole mergers have been converted to audio, it's natural to wonder what sound is really doing out there. And it becomes even more confusing when you encounter recordings labeled as the sound of a black hole or the voice of a galaxy cluster. The idea is compelling, but when I examine it carefully, the reality is much quieter and far stranger than that phrase suggests. Human intuition treats sound as something universal. We hear a collision and expect the same principle to operate anywhere else. Sound to us is tied to the very notion of an event, but the evidence we have today tells a different story. The universe is mostly empty, and sound in the technical sense requires something almost entirely absent from interplanetary and interstellar space: a medium. Air, water, rock, these materials transmit pressure waves. Space, for the most part, does not. Sound is simply a variation in pressure passing through a material. Your eardrum vibrates because the air around you is dense enough to carry those fluctuations. But in the space between stars, the density of particles is closer to a handful of atoms in a room the size of Earth. That is nowhere near enough to transmit a meaningful pressure wave. Even in the regions between galaxies, the density drops even further. So if a spacecraft exploded in open space, no sound would travel. There would be no auditory warning, no rumble, no echo, only silence. Yet researchers do talk about sound waves in cosmic structures, especially in galaxy clusters. A famous example comes from observations taken by NASA's Chandra X-ray Observatory of the Perseus Cluster, a vast region of gas surrounding a supermassive black hole roughly 250 million light-years away. Astronomers found that the gas in that cluster ripples in slow, giant pressure waves. These waves are indeed sound in the strict physical sense. They compress and expand a medium. But the frequencies are astonishingly low, far below anything the human ear could register. One of those wave cycles roughly once every tens of millions of years. To make that perceptible, scientists shifted the frequency upward, raising it by dozens of octaves. Only after that translation does the wave fall into the human hearing range. The resulting audio clip is not what a human would hear if placed inside the Perseus cluster. It is an interpretation, a mapping. The sound becomes something closer to data visualization than a recording. The same principle applies when gravitational waves are turned into audio. A gravitational wave is not a sound wave. It is a stretch and squeeze of space-time itself passing through Earth and altering the distance between mirrors in detectors like LIGO and Virgo. When the detectors measure that changing distance, computers convert that pattern into a frequency we can hear. The rising tone you may have listened to, sometimes called a chirp, is not the universe whispering. It is mathematics translated into sound. To visualize what's happening, I sometimes imagine a vast dark ocean with currents too slow for any creature to feel. A wave moves through it, but it does so with such an enormous wavelength that even a spacecraft drifting through the region would experience no noticeable pressure change. The wave is real, yet it is not perceptible. Only after compressing its scale by orders of magnitude does it fit into the narrow window of frequencies that our ears interpret as sound. This mismatch between cosmic data and human perception reveals a quiet truth about our senses. Our ears evolved to detect the rustle of leaves, the snap of a branch, the call of an animal nearby. They are tuned to survival in forests and plains, not to the movement of galaxy clusters. Our hearing range is a narrow slice of what pressure waves can be, and a narrower slice still of what the universe contains. The same applies to our eyes. Visible light is only a tiny strip of the electromagnetic spectrum. Beyond it are radio waves stretching for miles and gamma rays oscillating trillions of times per second. When I think about this, I'm reminded of how dependent we are on technology to extend what we can perceive. Instruments allow us to hear what the universe never intended for ears. They allow us to see what no eye could register. They convert scales enormous distances, slow vibrations, and visible radiation into something accessible. And each translation, while limited, brings us closer to the underlying reality. You and I live within sensory boundaries, shaped not by cosmic truth, but by biological history. Our understanding grows when we stretch those boundaries with detectors, telescopes, and algorithms. And each time we do, we gain a new perspective on what is happening out there. The recordings labeled as sounds of the universe are reminders of how much interpretation is involved in scientific communication. They are not mistakes. They are bridges between worlds of vastly different scale. When I step back from the idea of cosmic sound and look instead at the physics, a larger pattern comes into focus: collisions shape structure. They gather matter, tear it apart, build new stars, reshape galaxies, and send gravitational waves across billions of light years. And that realization leads to one final question. If collisions have shaped so much of cosmic history, could they also play a role in how the universe ends? Every collision reveals something about how matter moves, gathers, and disperses. And when I follow that logic all the way forward, I arrive at a question that has hovered over physics for more than a century. How will the universe end? Most people imagine a dramatic conclusion, something loud and violent, because the human instinct is to equate endings with sudden change. But the evidence we have today tells a different story. The universe does not behave like the objects we touch or the mechanical systems we watch break down. Its long-term evolution is governed by gravity thermodynamics and something more mysterious, the acceleration of cosmic expansion. Our earliest clues about the universe's fate come from the work of astronomers in the 1990s, particularly teams such as the Supernova Cosmology Project and the High-Z Supernova Search Team. By observing distant Type Ia supernovae stellar explosions with predictable brightness, they found that those supernovae appeared dimmer than expected. The simplest explanation was that the universe's expansion was accelerating. Instead of slowing down due to gravity, galaxies were being pushed apart more and more quickly by something we now call dark energy. Dark energy behaves nothing like matter or radiation. The best current evidence suggests it is a property of space-time itself, a kind of energy density that remains constant even as the universe grows. And because it stays constant, its influence becomes dominant over time. Galaxies move apart. Clusters drift farther from one another. The large-scale structure of the universe becomes increasingly sparse. If this acceleration continues, and that is still an open scientific question, the universe will grow colder and emptier as time stretches forward. Stars will burn out. White dwarfs will cool. Even black holes, according to Stephen Hawking's predictions, will slowly evaporate over timescales so long that they defy human metaphor. This scenario is sometimes called heat death, not because it is hot, but because all usable energy becomes evenly spread out. In such a universe, nothing new forms. There are no collisions left to sculpt structure. Another possibility involves the far more dramatic Big Rip, though it remains speculative. If dark energy becomes stronger over time, rather than staying constant, the expansion could accelerate so violently that it overcomes all forces holding structures together. First, galaxy clusters would drift apart. Then galaxies themselves. Much later, stars and planets. And in the final moments, even atoms would be torn apart. The timeline for such an event, if it were to happen, would be many billions of years in the future. Yet the idea is a reminder that cosmic evolution depends not just on matter and energy, but on the precise nature of dark energy, a component we still understand poorly. There are scientists who explore alternative futures. Some consider a slow decay of dark energy into other forms. Others look at models where the universe's expansion eventually halts and reverses, heading toward a big crunch in which everything collapses inward. At the moment, observational evidence strongly favors continued expansion, not collapse, but the discussion remains open because our measurements of dark energy's properties are still imprecise. Missions like ESA's Euclid telescope and NASA's Roman Space Telescope are designed to refine those measurements in the coming decades. To visualize the distant future, I imagine the night sky changing slowly over trillions of years. The Milky Way and Andromeda will have merged long before forming a new elliptical galaxy. But as expansion accelerates, all distant galaxies will slip out of view, moving away faster than light can reach us. Future observers, if any remain, would see a lonely island of stars surrounded by darkness. The cosmic background radiation would fade to near invisibility, stretched to wavelengths far beyond what any detector could register. Temperature differences would approach zero. Motion itself would lose meaning. In that remote future, collisions would become rare. Stars would no longer interact. Gas clouds would no longer crash into one another to spark new stellar nurseries. The universe would become quiet, not in a literal auditory sense, but in an energetic one. Without gradients of temperature, density, or motion, nothing new would emerge. You and I live at a time when galaxies still collide, when stars still form, and when gravitational waves still ripple across space. In the vast calendar of cosmic history, that window is small. Understanding this does not diminish our place in the universe. It clarifies it. We are part of a phase defined by motion, contrast, and complexity. And that in itself is remarkable. With that, we reach the end of our journey through cosmic collisions. But the story they tell carries us naturally toward reflection because every collision, every ripple, every drift has played a part in shaping the cosmos we briefly inhabit. Thank you for staying with me through this exploration. I hope the calmness of the journey allowed the science to settle comfortably into your thoughts. And as you move back into your own night, I hope you carry with you a sense of how deeply connected we are to the motions and interactions that shape the universe.